You know how your phone can instantly blur the background in a photo? Or how a simple filter can make an image suddenly look incredibly sharp? It really does feel like magic. But today, we're going to pull back the curtain. Just look at these two pictures. On the left, you've got this beautiful, clear photo of a dog, and on the right, well, it's the same dog, but it looks like it's straight out of an old video game. How in the world does a computer get from point A to point B?
That's really the big question here, isn't it? What's the actual process that lets us blur, or sharpen, or totally pixelate a picture with, just a single click?
Well, the answer isn't some super complex, artsy tool. It's actually just math. Pure and simple mathematics. We're talking about a few elegant operations that can totally transform an image, one little pixel at a time.
So, to really get the math, we first have to get on the same page about what an image is to a computer. Let's peel back those layers.
So if you zoom in, like way in on any digital picture, you'll find it's just a simple grid. Each of those tiny squares of color, that's a pixel. It's the absolute fundamental building block of every single image you see on a screen. And here is the absolute key. Each one of those pixels isn't just a color. To the computer, it's a number. It's a value that tells the machine exactly how bright to be or what color to display. The entire image is just one massive grid of numbers.
So there's the secret. A pixel is just one dot of color that's defined by a number. So if you want to change the image, all you really have to do is change the numbers.
And that brings us to the engine room of all this, a technique called convolution. This is the mathematical magic that creates all those filter effects we know and love.
At its heart, convolution is basically a neighborhood watch program for pixels. To figure out the new value for any one pixel, it takes a look at that pixel and all the ones immediately around it, and then it does a little bit of math.
But how does it know what math to do? Well, it uses this little thing called a kernel. You can think of a kernel as a recipe. It's just a tiny grid of numbers, and it tells the process how to weigh each neighboring pixel, basically how important each neighbor is in the final calculation.
So this kernel, this little recipe, it literally slides across the entire image, one pixel at a time. And at every single stop, it centers on a pixel, does its calculation with the neighbors, and then spits out a brand new value for that center pixel in the new edited image.
All right, let's zoom in and look at one of those stops. So here on the left, you've got a 3x3 block of pixels from our original image, each one with its own number. And next to it, there's our kernel, our recipe for how we're going to mix these all together.
And the process is actually really simple. You just take each pixel's value, multiply it by the number in the matching spot in the kernel, and then you just add all those results together. That's it. It's just simple multiplication and addition repeated for every single pixel in the picture.
Okay, so if the math is always the same, how do we get totally different effects, like a blur versus a sharpen? Well, it all comes down to the numbers we decide to put in that little kernel recipe.
For example, if you use a kernel where all the numbers are positive, say a grid of all ones, it basically just averages the values of all the neighboring pixels. This smooths out any sharp differences between them, and what you get is a blur.
But watch this. If you change the recipe, if you use a kernel with a big positive number smack in the middle and negative numbers all around it, you get the complete opposite effect. This kernel actually exaggerates the difference between a pixel and its neighbors, which makes edges pop and gives you that sharpening effect.
I mean, this just shows the power of the kernel perfectly. The blur kernel averages everything out for a smooth look. The sharpen kernel subtracts the neighbors to make the center stand out. It's the exact same process, but you get two completely different results just by changing a few numbers in that tiny grid.
Now, sliding a kernel across millions of pixels works great, but for really big images or super complex blurs, it can be kind of slow. So computer scientists came up with a powerful shortcut by looking at images in a completely different way.
What if, instead of seeing a grid of pixels, we could somehow see the underlying patterns that make up the image? The visual equivalent of its DNA?
Well, we can actually do that by thinking in terms of frequency. You can think of any image as a mix of different spatial frequencies. Low frequencies are those slow, gradual changes in color, like a smooth, blurry area. High frequencies are the rapid, abrupt changes. Think sharp edges on a building or the detailed texture of fabric. And this is where it gets really, really cool. Up top, we have our blurry dog. Below it, that's its frequency spectrum. It's created by a math tool called a Fourier transform. and it basically converts the image from the world of pixels into the world of frequencies. All that bright stuff in the center represents low frequencies. And since the image is blurry, it makes perfect sense that it's just dominated by those slow, gradual changes.
So why do all this? Why go through the trouble? Because of a beautiful mathematical shortcut called the convolution theorem. What it says is that the slow process of sliding a kernel over every single pixel, that's convolution, is the exact same thing as doing one simple multiplication in this frequency world. It's a massive, massive time saver.
So to create a blur this way, instead of using a kernel, we just take our image's frequency map and get rid of the high frequencies, all those sharp edges. Then we just transform it back into a normal image. And the result? The exact same blur we got with convolution, but a lot of the time, it's calculated way, way faster.
So we've seen how these really simple operations, just multiplication and addition, when you apply them in a clever way, can fundamentally change our visual reality. It really makes you wonder, if this basic math is the secret behind every photo filter and video effect, what other invisible mathematical structures are shaping the rest of our digital world?